Swayam Prabha. Digital India. Educated India.
Hello students, welcome back to the discussion of principles and chemical applications of thermodynamics, and here in this lecture I will continue our discussion on the application of chemical potential using the principles of thermodynamics of open systems. Now let me remind you that in this discussion we are going to use the fundamental equation of chemical thermodynamics, which is applicable to open systems, whereby the Gibbs free energy of the open system is expressed as a function of temperature, pressure and composition of the system. Now, if I think about, in addition to temperature and pressure, we have introduced here the chemical potential. I understand that the chemical potential is defined in terms of a partial derivative of G with respect to the number of particles of the ith type, keeping temperature, pressure and number of all other particles constant. And we have also seen that the consequence of using this definition and combining it with the other relations in thermodynamics gives us the Gibbs-Duhem relations. And we have seen how these relations can be used to work out the thermodynamics of an ideal gas mixture. Now, in today's lecture, we will now discuss the chemical reaction equilibrium. So let me put you in the same perspective of how we plan to use the concept of transfer of matter for a chemical reaction. So I'm going to put chemical reaction equilibrium in the same generalized picture as mixing of ideal gases and phase equilibrium. Now let me remind you that when I had mixing of a set of non-reactive ideal gases, then we talked about transfer of matter from one region of the system to the other. Now when I talked about phase equilibrium, I was talking about transfer of matter from one phase of the system to other because the system under the given condition of temperature and pressure is unstable in one phase, and thermodynamically it will have two phases coexisting in equilibrium. So that is the situation of phase equilibrium. Now, if I talk about chemical reaction equilibrium, as you understand, this is going to be a more difficult situation compared to either mixing of ideal gases or the phase equilibrium of a pure substance. Why is that so? That is because now I have a transfer of matter from one chemical identity to the other. So basically the situation that I'm talking about is, let me say that I start with the green reactants and the orange reactants separated under a given condition of temperature and pressure. Now if I allow them to mix, what will happen? Not only that, the green particles will spread out all throughout the box. The orange particles will also spread out all throughout the box. And in addition, because of a chemical reaction taking place between the green balls and the orange balls, new species will appear in the final equilibrium mixture. Now once again, let me highlight in this situation what we have as the transfer of matter from the reactants to the products. So, what do we have here regarding the particles of type blue in this situation? I see that my initial mixture had a few blue particles. Now, in the final equilibrium mixture, the number of blue particles is not the same as before. So, now I have a less number of the blue reactants. Similarly, depending on the chemical reaction, I will see that there is a change in the number of the orange reactants as well as I go from the initial mixture to the final equilibrium state. And not only that, now I have a situation where initially the product, the pink squares were not present in the initial mixture, and now I have these components appearing in the final mixture. And therefore, as far as each of the components are concerned, I understand that each of them are undergoing a change in their individual numbers as I pass from the initial state to the final equilibrium state. Therefore, whenever I am describing the chemical reaction equilibrium, I must take into account two factors. One is the transfer of matter from one chemical identity to the other, and the second one is mixing of these different chemical species in the final reaction mixture at equilibrium. With this picture in mind, let us now try and derive a description of chemical equilibrium in terms of chemical potential and show how we develop a single thermodynamic quantity called reaction Gibbs energy to describe the direction of spontaneity of a chemical reaction and the condition of equilibrium. Now, let me start by defining the reaction Gibbs energy. This is given a symbol like this. Now, let us consider a very simple chemical equilibrium. So, I have the reactant A, I have the product B, and in chemical equilibrium, A is equilibrated with B at a given temperature and pressure. Now, let me say that I take this equilibrium reaction mixture and I allow the system to undergo an infinitesimal amount of chemical reaction such that A undergoes an infinitesimal amount of change d xi and it goes into B. Under such circumstances, I must be able to say that since the reaction has happened, there will be change in the number of particles of the species A as well as the species B. Now, as you see that here I am adopting the number of moles as a convenient unit to represent the number of particles present in the system. Therefore, as a result of d xi amount of reaction taking place, I will have dNA, that is the infinitesimal amount of change in the number of moles of the species A, and as a result there will be dNB, that is an infinitesimal amount dNB of a change in the number of particles, number of moles of the species B. Now, by definition, since this is my balanced chemical equation, if dNA is equal to minus d xi, Therefore, I must be having dNb is equal to plus dxi. In this case, I am once again trying to highlight the fact that xi is the extent of reaction and its units are in moles. And here the reaction Gibbs energy is defined as follows. This is the partial derivative of the Gibbs free energy at a given temperature and pressure with respect to the extent of reaction. Therefore, delta Rg, that represents the variation of the Gibbs free energy of the reactive system as the reaction progresses, which is indicated by the quantity xi, and delta Rg is defined at a given temperature and pressure. Now, let me see how chemical potential and reaction Gibbs energy can be related to each other. For this equilibrium A reversible B, if the reaction advances by dxi, then I can always use what I know from thermodynamics, what is going to be dgTp. So dgTp, I know that in this case is going to be mu A dNA plus mu B dNB, simply because dt and dP are individually equal to 0 as I am carrying out the chemical reaction at constant temperature and pressure. Therefore, dG arises essentially from dNA and dNB. And here, if I replace dNA and dNB in terms of dxi by noting that dNA is equal to minus dxi and dNB is equal to plus dxi, I put it back in this expression and this is what I get. Very simple. Therefore, I can say that what is delta Rg? If I take this equation dgTp equal to mu b minus mu a into dxi, then del g del xi Tp is going to be mu b minus mu a. Therefore, I can conclude that the reaction Gibbs energy is nothing but the difference between the chemical potential of the product and the reactant. This is very important at the composition of the reaction mixture. Now, as you see that here reaction Gibbs energy is a function of temperature and pressure. Why is that so? That is because each of these chemical potentials are functions of temperature and pressure themselves. And what I find is that by the Gibbs to Hem relationship, chemical potentials will be related to the composition of the reaction mixture. And therefore, as I understand, it is very important to mention that at a given temperature and pressure, at the composition of the reaction mixture, the reaction Gibbs energy is the difference between the chemical potential of the product and the reactant. Now, if I take a very simple example, I have 3 moles of A1 producing A2. This is the balanced stoichiometric chemical equation, and I understand that at a given temperature and pressure, the species A1 and A2 are in equilibrium with each other. Now, if I do a little bit of an algebraic reorganization, I can write down the stoichiometric chemical equation as A2 minus 3A1 equal to 0. So what is it that I have done? All I have done is I have written down the balanced equation as A2 equal to 3A1, where A2 is my product and A1 is my reactant. And then I have algebraically taken the right hand side to the left hand side, and this is how I write this equation. Now, what is the difference between this form of the equation and this form of the equation? You see that each species present in the chemical reaction, whether it is the reactant or the product, they are present on the left hand side of the equation. And also we find each of them have a coefficient which is nothing but the stoichiometric coefficient as given by the balanced chemical equation. But there is a difference. The difference is the coefficient of products appearing in this equation is positive and the coefficient of the reactants appearing in this equation is negative. So all we have done is we have rearranged and written down the balanced chemical equation in such a way that I will retain all the stoichiometric coefficients of the balanced chemical equation, but the coefficients that appear here in the algebraic chemical equation is that the coefficient of products are positive and coefficient of reactants are negative. Let us next examine the change in Gibbs free energy. For this equilibrium, if the reaction proceeds in the forward direction at a given temperature and pressure such that the reactant has undergone dN1 reduction by dN1 moles and the product has gained dN2 moles, then dGTP is going to be written as mu1 dN1 plus mu2 dN2 as I have written over here. But simply because I can think of this infinitesimal advancement of the reaction by this amount d xi, and since the change in the number of moles of the reactant A1 is related to that of A2, I can very easily say that dN1 is going to be proportional to d xi and dN2 is also going to be proportional to d xi, but in this case dN1 will be dependent on this number and dN2, so depletion of the number of moles of A1 by the amount d xi actually will depend on the number of moles present in the system to start with. And what decides this number? The balanced stoichiometric equation. So I can have, for the same extent of reaction, for every 3 moles of A1 reacting, there will be 1 mole of A2 produced. Therefore, if I have a very small amount d xi of reaction, then dN1 is going to be minus 3 d xi, while dN2 is going to be plus d xi. And therefore, I can combine these two relations now and write dGTP is going to be mu2 minus 3 mu1 into d xi. So can I now get the reaction Gibbs energy? The answer is yes. So the reaction Gibbs energy which is defined as del G del xi Tp is given by mu2 minus 3 mu1. So as you see, therefore, if I know how to write down this equation, I can immediately write down the reaction Gibbs energy in terms of the chemical potentials of the species present in the chemical reaction mixture pre-multiplied by the coefficients which appear in this algebraic equation representing the chemical reaction. Now let me take one more example. Now I have another set of chemical equilibrium where 3 moles of A1 reacts to give 5 moles of A2. So what is the balanced chemical equation for this reaction? The balanced chemical equation for this reaction is 3A1 equal to 5A2. So if I now try to rewrite this equation in the form of the algebraic balanced chemical equation, what shall I write? I shall write 5A2 is equal to 3A1 and then take this on the other side and write 5A2 minus 3A1 is equal to 0. So I understand here A2 is the product and A1 is the reactant. Okay. So once I have this in mind, then I'm going to use this algebraic equation to write down the form of reaction Gibbs energy. So let me start from this balanced algebraic equation. The change in Gibbs free energy as before is mu1 into dN1 plus mu2 into dN2. And if the reaction advances by d xi, now I know that dN1 is equal to minus 3 d xi that I learned from here, and dN2 is going to be plus 5 d xi, for which I have once again used the same equation. And therefore, I can say that dGTP for this reaction is plus 5 mu2 minus 3 mu1, this whole difference multiplied by d xi. So what is the reaction Gibbs energy? That is given by del xi del Tp, which now is given by 5 mu2 minus 3 mu1. So let us now talk about chemical potential and reaction Gibbs energy for the generic situation which I have represented here. So the very first step would be writing out the algebraic equation in terms of capital A1 and capital A2, which are the reactants and the products. So now you see that I am collecting the coefficients here in terms of these, and I understand that whatever appears as these coefficients are positive if it is product and negative if it is a reactant. And therefore, in general, I can say that for any given chemical reaction that we have seen, the balanced stoichiometric equation can be written in a form like this, where I understand nu2 is a positive quantity and nu1 is a negative quantity. With this in mind, let me think about the change in Gibbs free energy. If the reaction advances by d xi, in that case dGTP will get converted to dN1 with dN1 equal to nu1 d xi and dN2 equal to nu2 d xi. dGTP will be now given by mu2 nu2 plus mu1 nu1, this whole summation into d xi, and therefore the reaction Gibbs energy is going to be given by mu2 nu2 plus mu1 nu1. Now, as you would understand that you might be a little confused here, saying that initially I was talking about the reaction Gibbs energy as a difference in the chemical potential of the reactants multiplied by the coefficients in their balanced chemical equation. But here I am writing the right hand side of this equation as a summation. So is there a conflict? The answer is actually no. Why is that so? Because all the reactants that I see here, the new one is going to be a negative quantity. And therefore, by adopting this, incorporating the sign in the stoichiometric coefficient, now in general, for the equilibrium involving more than one or two or three reactants and products, if I can write the balanced chemical equation in the form of an algebraic equation like this, I can immediately write down the reaction Gibbs energy as a summation over all I, mu I, nu I. So let me remind you once again, if I have several species like 3 reactants giving you 2 products or whatever have you, you can always rewrite the balanced chemical equation in a form like this and recast it in a form like this, where you assume that for a reactant, the coefficient that appears in this equation is going to be positive and the coefficient that appears here is going to be negative. And then all you will have to do is write down the reaction Gibbs energy as summation over I, mu I, nu I. But how does it help? How does it help us in predicting the direction of spontaneous change of a chemical reaction? And how does it explain the attainment of equilibrium at a given temperature and pressure? So keeping this definition in mind, we now have to understand this fundamental question. Till now, for a given composition of the reaction mixture, we could define G as a function of Tp and the composition of the reaction mixture. But now, as I have this chemical equation and I am perturbing it only a little at a given temperature and pressure and allowing it to undergo a change in every species by this infinitesimal amount d xi, in order to understand how the Gibbs reaction energy varies with the advancement of the reaction, I need to understand how the Gibbs free energy varies with respect to xi. Or in other words, instead of this, I need to understand how G varies as a function of temperature, pressure and xi when I keep T and P constant. In order to understand this, let me consider this picture where I have plotted the Gibbs, I am going to plot the Gibbs free energy of the system at a given temperature and pressure as a function of advancement of reaction xi. If I had the pure reactants xi equal to 0, and therefore let us say that this is going to be the value of the Gibbs free energy for the pure reactants. Now when xi is the maximum value, then I will have only the pure products, that is 100% conversion of the reactants to the products. Then again, I can think about this point as the one where this represents the Gibbs free energy of the pure products, right? Therefore, in between, let us say that I am at this point shown by this red dot, and here what is going to be the composition of the system? Here, for the ith component of the reaction mixture, I will have Ni is equal to Ni initial plus nu I xi. Therefore, I can very easily write that for any composition at T and P, I know G is summation over Ni mu I. Where did we get that from? Yes, you are right. We have got this from the Gibbs-Duhem relation. Now, whenever I have an intermediate reaction mixture, I understand that Ni is a function of xi. And therefore, for any composition and temperature and pressure, I do expect G to be a function of xi. So in our next lecture, we are going to derive a functional dependence of G on xi and see how it varies with xi at a given temperature and pressure. Thank you.